Then, welcome to the fifth session of the WiNoDa webinar. We just heard last time was a short introduction to the deep learning idea or the underlying, roughly speaking, general ideas that actually make what deep learning is today. We dived a little bit into the technology, a little bit into the bigger picture, and I gave some ideas about the used algorithms there. If you missed it, don't worry too much. I will give a very short version of last week in a second. However, today is then a bit about trying it out yourself. If you want to, at least, you can also just watch me doing it. But if you don't have then the background from last week or don't have any background, then there might be some bits and pieces that are a little bit harder to grasp. But I'll try to give you the main ideas anyway. And maybe the effect of what we're then doing today is already enough to be motivated to dive on to this world of deep learning, maybe also watching then the last week's seminar or some other material that I will also give references to. Slides of today will be available under this link. I will paste it also to the chat. So actually, I can do this now, then we don't forget it. Chat here. So there you find a PDF version of today's slides, and whenever necessary today, I will also post other links that will lead you then to the notebooks that we're using today. All right. Now, what can you expect today? As I already said, there will be a very short introduction again to the idea of deep learning in a minute. That more or less summarizes last week's session. This is not intended or planned to give you really the full-time overall idea, but just that you maybe remind yourself about the material from last week, or if you haven't seen last 2 weeks, so last session, if you haven't seen that, then just give you some ideas and details about what's happening. Then we will go through 3 hands-on examples. Again, I will give you the links to the notebooks, similar in the last hands-on session we had. And then you can play with that yourself or follow what I do. Or if you don't want to do anything at the moment, then you can also just watch me going through the notebooks and explaining them as we go. And then there will be hopefully enough time also for questions in between, or if you have any comments about it, that we can also discuss that. Good, let's dive into it. So first, quick reminder or summary from last week. A neural network is the underlying technology of what today is called deep learning. A neural network is some kind of algorithm or method or machinery that can do, for example, classification. Classification in this very particular example here is that you present this neural network, this algorithm here, some kind of input, in this case, an image of a cat. This neural network analyzes this image and prints out a label or something in a written form that is then, hopefully the same thing as was in the image. So a cat here, or if you would present it to a car, then it should write car here, and so on and so forth. So that's the rough idea. Often it's referred to as kind of a black box, what's really happening here. That is today only partly true. There are enough algorithms and method to at least partly understand what the neural network is doing. One can visualize the processes that happen inside. One can try to understand what the neural network actually is reacting to when, for example, cat image is presented. You can visualize somehow where the neural network takes the information from. So maybe then the eyes are important and the ears, and the dogs have a little different symmetry, for example, in this case. So you can visualize the things and make some kind of understanding out of it. However, it is still, in particular, with these very large networks that we're using today, partly still a black box, although the technology underlying can be analyzed and then understood mainly. Good. So more or less general definition, a artificial network is a interconnected group of nodes that are these circles here. And the whole thing, the whole setup is supposed to kind of mimic the human brain, also in your brain, you have these neurons or nodes, and they're connected to each other through what we depict here as arrows, so some links or connections. And some of these links or connections are stronger between two nodes, some are weaker. And overall, billions and billions of those then allow to make decisions or even think, at least in human sense, or do it on a much more broken down level in these artificial networks, where they can be used, for example, for this classification task. Good. What we went through a little bit in more detail last time was then how you, what we call, train a neural network. And the main idea one needs to understand is that a neural network can do more or less everything you want it to do. The question is, how complex does the network have to be? And how do you then make this complex machinery to do what you want to do? And the key technique here is what is called training. And what the training at the end boils down to is that you present some kind of input to this neural network. And again, this is now super simple, so usually that's much larger and much more connection, but more nodes. And then you check the output of the network, so what the neural network thinks the answer is. And then you can, if it's wrong, then you can trace back through the network, and you can more or less analyze where most of the mistake has been made. So maybe some connection was wrong, or the weight of the connection was wrong, and you can, through mathematical algorithms, find these things, and then you can correct these parts of the network or bring it towards a direction in which the answer would become better. So that's the training part. And today we will see more or less how to set up this kind of network and then really do the training for some simple examples. But again, you need to understand that there's always two things. One is constructing a network, so more or less how many nodes should be there, how many connections should be there, how many what we call layers. So this is a layer of network, that's another layer of the network, that's the input layer, that's the output layer. How many layers should be there, and then how to perform this training. And again, training is presenting examples, checking the output, and then correcting for errors. And at some point in time, if your network was complex or large enough for the task you wanted to do, then the output will more or less be perfect. Also then, just for a reminder, that's what I presented last time as a super simple example where I want to train some neural network to understand if my sensors in my plants show a particular value, that the neural network learns whether the soil condition is either good or bad. And then when I change then my soil and the sensors show something else, then I would like the network to tell me whether this is now a good condition or good soil for my plants or not. So I provided always input. Then there are these weights that have to be learned through this training process, and then I have some output here that in the best case scenario is then giving me some insights about how my plants feel. And then I showed you also a little bit, at least, this training process. And the training process, again, is described, consists of I present this data with this correct label, and then this data with this correct label, and then this data with this correct label. And then I always check whether the presented input matches the label I want. So in this case, I presented the 6.4, 2.8, 1.7, which in this example is the sensors for my plant. I put this through the network. I find out that the current answer that it gives me is 0.9, should have been 1 because I have labels of 0 and 1. So the error is minus 0.1. And this error now I can analyze and see where the most in the where in the network the most part of the error were made. Then I correct these parts of the network, and then next time the result will become better. And this process you then repeat thousands, maybe millions of times, and every single time your network becomes kind of better, at least in terms of the data that you try to train it with. And at some point in time, you then have a trained network then you can use to fulfill the task that you're interested in. And this task can be as stupid as this plant example, or as complex and complicated as understanding human language or natural language, or analyzing images and other examples we saw last time. And then this was the final slide from last time. So just again, super simple summary of what's happening. So you have some training data set that you train it with. Then you train some kind of convolutional network. You have some output at the end. You check whether the output matches the input. If not, you correct for this error. Train with the next image, and this you can do then, and yeah, until basically it becomes better, or doesn't get better anymore, and then you can do task as in as we discussed last time, segmentation of images or feature and object detection, or this image captioning, where you present the network a image and ask it what you can see of the image. You can generate images with this, or you can even play games, Go and chess and then whatnot, for which are these neural networks already available. Okay, so that was the super short reminder. And now we directly actually jump in our examples. So I have 3 examples today. First one is super simple hello world example, and it's supposed to give you really just the getting started idea of, okay, cool, in the notebook that I'm using, or in the computer that I'm using, or in the environment that I'm using framework, this is the super basic things that I need, such that I can actually get started with some neural network, or later on we will see deep learning analysis. 2 things first. This was the slide we already saw in the last hands-on session. We will use today this Colab framework that's provided by Google. It's free to use, but you need a Google account. If you click on this link here, then you will be presented with the starting page of the Colab framework. And there you can create or use what we call notebooks. And the notebook is nothing more than just I can put code fragments. I can execute this code fragments and see immediately what happens to it, as in like what's the output of the code that I just wrote. I can add also annotations to it or explanations. You will see in a minute how it looks like. And I can then step by step build up not only my big program that at the end I want to have, but I can go through each of the steps and make it better, improve it, change it, and then see how my whole program actually is evolving over time. I put here also some link. There are hundreds of others, probably thousands, where you can get a quick introduction to this Colab idea or framework. But yeah, if you Google for it, then you will get many links where you can get more information. And then the thing that is important for today, which wasn't too important last time, Google offers you usually that your programs are running on a normal CPU. So a normal, what you have a compute processor on your laptop or your desktop PC or whatnot. And this is usually fine for most machine learning algorithms that you can use. But for the deep learning or these quite compute intense neural network architectures, you usually want to use a GPU, so a graphics card, basically. Graphic cards have been developed for playing games. Today, they're mainly developed for running artificial intelligence programs or code. So what you need to do is, if you open your Colab notebook, you have to go to runtime or Laufzeit in German. You say change runtime, Laufzeit in German, and then you can select here a GPU. The only thing that if you don't pay for the Google Colab account is that you can only run one program at a time. So you can only use one GPU at a time. And the second downside is that if you don't pay for it, as you also could, then sometimes these GPUs are actually rather slow. However, they're for free, so usually not a big problem. However, if you use GPU settings and run deep learning code, then it's much significantly faster than if you only CPU code. So make sure that usually on every new exercise or every new notebook you're creating, this is still set to GPU. Okay, first, now I'll need to change my whole screen. So let me briefly stop this and go to the whole screen setting. It should be this here. Okay, you see now on the left-hand side the presentation, a little smaller, and on the right-hand side the notebooks that we will work on in a minute. The first thing we need is, I'll give you the link to the code that we are using now if you want to go along with me or just want to use it in your own pace later on. So we start with this hello world example here. And this does the following. First, now it opens it. Again, these are now these notebooks. This one has been written by Elvis Saravia. There's also a couple of links that you can get more information on. And also at the end, there's also a couple references if you need more information. So this is done by these people, and I just tuned a little bit so that we can use it directly in this course here. Okay, so now what is a notebook? Well, first we check whether our runtime is set correctly. So we go to this runtime or Laufzeit in German, we change it, we know, or we see already, okay, cool, it's the GPU setting, so everything is good. And now, just if you haven't seen a notebook before, again, a notebook consists of text items, if you want, in which you can describe something or put images even. And then these gray ones are code lines. We go in a minute through what they mean, but just that you can have description, you can have real code, and the code can then be always executed. And then whenever the code is producing something, then directly under it, there will be the output of the code. Okay, so what's happening? First of all, let me remind you of the AI feature that Google provides you with also in these notebooks. If you click on this Gemini button here, then it opens this kind of sidebar. And here you can directly prompt whatever you are interested in prompting. For example, what we can do now is we can just copy this code here and say, explain this code, and then give it the code we just copied. And then it goes also as similar to what I would do now, goes through it and explains you really what's happening in this code or in these cells here. You can also ask other questions or follow-up questions. What is Torch and so on and so forth. For now, I will take over the role of this Gemini AI bot here. But always remember that with this functionality, it's actually really powerful. You can go through code and ask hundreds of questions about stuff you might not have understood yet. Okay. As we also saw in the first hands-on session some weeks ago, that today you don't really program as we used to 25 years ago, which is you would, for every algorithm or every method you would write, you need to write everything from scratch. Everything you want to do, you need to code into, or you have to write into your source code and do things. Today, we usually program using libraries. Libraries means that someone else has programmed something and you're more or less using this code now. And you don't even need to understand these thousands and thousands of code lines. You just know how to use basically the more higher up methods. That is, you can use a particular method that the person wrote. Maybe the person wrote a method that's saying, create an image with dog, and then you don't need to really understand what the person did for the coding there. You just call this method and you get the image of a dog because that's how we code it. So we use libraries. And one important library for deep learning is called Torch, or pyTorch. And there are others which we will not use today, but you can happily check them all out. Some are better to use maybe for your kind of programming experience. However, pyTorch is one of the bigger or main ones. So that's why in the first step, we use this import statement here, which means, dear code interpreter, please use or find the Torch library that is hopefully installed in the system. If not, you can install it manually and make it available in my program. So I click on the little play button here while this circle here is spinning. It's being executed, so this cell here is being executed. So what happens now in the background, you can also see down here in the status of the window. And yeah, it's now doing something, we're calling some code. And at the end, it's supposed to print the version of the Torch library we're using. So we see a result of this executed cell. We see we're using the 2.5 version or 2.51 version of Torch. Okay, so we now have Torch available. So deep learning algorithms available. And for the next part to understand, it's important to more or less understand this image here, which I also had at the slides earlier. So the idea is that you have some kind of model. We will use, as we discussed, a neural network, and later on in a deep learning or deep neural network for learning mainly. The model has a couple of components, if you wish. It has the architecture, so it's full what we refer to hidden layers. You saw that earlier. was on this slide here. So this was one hidden layer in our neural network from this example. So we have the input, the output, and then one or many hidden layers with 3 or more, much more nodes in it. So we know the architecture of the network. We need some kind of loss function. The loss function was connected to this when we said how big is the loss at the moment that we're having, so the mistake or the error. So we expected here a 1. And then the loss function that we used here was some Euclidean distance. So basically just the difference between the value we wanted and the value we have at the moment. So this is some kind of, we can have other loss functions. For now, we're usually using the Euclidean metric, as we call it. And then you use some kind of optimizer. And this is basically how should the weights change? What should be the algorithm to change the weights? And how to find the new weights. Should it be very strongly or just a little bit, and in which direction should one look, and so forth. But this at the end is done under the hood. You just need to know that these are some kind of components because they will always now show up again. And if you change some of them, then your results might become better or worse, or it becomes slower or faster to train. Okay, so that's a model. And as we discussed also earlier, you need some data that you feed your model with to train it. And then once you're done with this and this model is trained, you can just use the model and use it to do some prediction, for example, as we said earlier, also for the cats and dogs, or whether my soil is good or not. Okay, good. For now, we look actually at some data that we want our neural network to learn. Comes in a particular format. In this case, it's XY coordinates or XY values. So if I put in a -1, the output should be a -3. If I put in a 0, the output should be a -1. If I put in a 1, the output should be a 1, and so on and so forth. So we just have this data now and have it available such that our neural network can learn it. We look at the size of our input vector. So we have 1, 2, 3, 4, 5, 6 samples. That's a 6 here. And they are one-dimensional, as we call it. So we give in one number and you get one number back. Good. Then we now introduce the model that we want. We only want to have one layer, so one of these layers here. We want to have one input node, so not 3 as in this example, but only 1. And we want to have one output node in our inner layer. So we have basically a network that has this input, has this middle thing here, and one output at the end. So that's how we structure our neural network. So the most simple you can think of. We also execute that. With this, we have built a neural network. That is it. Our model is now really only one layer with one node in the middle as an input, and then one node in the middle, and then output is also 1 because we know the data from. Now we need, as we said earlier, that was from here, we need some loss functions. So how do you want to measure whether it's correct or not correct? This is our what we call MSE loss here. Again, similar to some Euclidean metric. And we need some optimizer algorithm. So at the moment, we want to use what is called stochastic gradient descent, which more or less means wherever the error is the largest, go first into that direction and try to correct it. And we can we can also set some learning rate. If this is larger, then there are larger jumps the method is using to try to correct the error. So it will try larger corrections. If it's much smaller, then it will be much more fine-grained at finding a solution. So there's also some tuning parameter here. Usually 0.1 is a good value, but sometimes you might just want to play around with it to see whether your model then learns better or worse. Okay, this loss and optimizer is usually just standard. So for many tasks, you can just use it as it is. What you would change then, and we will do this in the next hands-on part, is to change the architecture of the neural network here. So maybe with more nodes in a layer or even more hidden layers in our network. And this will be more or less always like this. So this is something we can usually use as a standard. Okay. So now we set up our model. We have created the model now, basically. And now we want to train our model. And the training is exactly as I said before. We put it into the training mode. We give it, we tell it the output. We tell it the input, so the data that we had here. So it was our x and y's here that we gave it. So x is always our input, or y is always our output. Then we calculate the loss, we optimize it, and we have the next version of our model. So each of these blue highlighted parts here is one step in the training. So I presented one of the inputs that I have, or at the moment, actually, the whole tensor that I have, so the whole list here. I present that, go through it one by one, calculate the error, adjust our weights, and then do this over and over again. In this example, I do it 150 times. And when we run this now, then what happens is that it will do this 150 times, always presenting the input, checking for the output, correcting the weights, doing it over and over again. And then you will see a list popping up now where the loss or the mistake that our model makes will become smaller and smaller and smaller. And if that happens and everything is good, our model is then trained and becomes better all the time. Sometimes you might see situations where this loss for some weird reason becomes larger again. And this means that your model is becoming too overtrained, as we call it. And this more or less means that it cannot generalize well anymore. So it's mimicking something like learning the values by heart. But whenever you have a little bit different values, it cannot actually predict them anymore because it just learned and memorized the input. So we click now on play. See what's happening. You see here it starts with a loss of 5 point something. That was in the first epoch or the zeroth epoch. And then the loss became smaller and smaller and smaller. And then at some point, nothing changed anymore. So it reached more or less the perfect configuration of the weights. And now what you can do is that you can ask the value, that's the trained model, and you ask, okay, if I give you 10 as an input, what would be the output? And what is happening here in the first one, you can see the values. I'm actually a little confused because I had a version where I was having this already corrected. Never mind. So the point is that the function that is underlying this data comes from here. So that's the one this is based on. So this is the function where this data is generated from. So y equals 2 times x minus 1. So you can see here 2 times 4 minus 1 is 7. So there should be a 7. And 2 times 3 minus 1 is 5, and so on. So if you now take this and ask the neural network, okay, you are trained now, so I would like you to answer the question for 10, then we can calculate the correct answer. The correct answer should be 2 times 10, so 20 minus 1, 19. And if we run this now, we'll find the correct. Yeah, that is not really true. And this is because the model is not, it's perfectly trained on the data it has seen before, but it's not really trained on the everything else that follows from it, but it's getting close. So we can also try it with whatever, 3 here, and then run it again. And the result is 5 point something, so it's already better. So it should have been 5, it's 5 point something. We can take a 2 here, and it's 3.4. It should be 4 minus 1 is 3. So you see the results are not super wrong, but they're also not super great. So it goes to the right direction, but it's definitely not yet perfect. But the point is, through a little bit of training, it is going towards something. So it's really going towards the direction that we want. And now one would play with the idea of okay, can I make the model more complex? Can I use different loss functions maybe? Can I use different optimizers or so? And maybe I just need more data to train the model on. And this is basically what we will do in the next example, to just see and play now with the complexity of the networks and what we can do with it. But for now, this Hello World example gives you really the smallest building blocks you need to build a neural network. You just need to give it the architecture, you need to put a loss and optimizer function, you need to give it data, and then this is then always the same, train it, correct for the errors that were made, and the model becomes better over time. And how good it can become depends on the data you give it, and yeah, well, on these settings here, the loss and the optimizer. But this usually doesn't have a too big weight on what's happening. So usually more or less the architecture or the structure of the network is what will make the neural network better or worse after you give it enough data to train. Okay. If there are spontaneous questions, then please put it to the chat and I can react to that. I will check every now and then whether someone wrote something. If not, I will jump to the next example. And the next example, I will leave it now on this screen next to each other. So the next example is going back to something we saw also in the last session and then the last hands-on session. And the point was that we were thinking or discussing, or I was presenting, the more or less classical machine learning approach versus the new or current up-to-date or state-of-the-art deep learning learning approach. And in the more classical version, the point was that you have some input, that's clear. And then, and that's the difference, you need to select some kind of model. So you need to say, okay, I want to have a linear regression or non-linear regression. I want to use some support vector machine or some tree-based method, or I want to use whatever else is out there. So you need to select an algorithm and also the features that the model should learn. So maybe by features we mean, do you take the whole image as an input, or do you first look whether there are circles somewhere and how many of them, and that's used as the input. So you need to define a lot of things. If you define the right choice, or if you happen to have the right choice, so you have the right input features and a good model for your task, then you can parameterize this, and you can then also use it on available data to make it better, or to fine grain it basically to your task. Then you can do some kind of say classification, for example, and you get some output. So this all works, but it requires a lot of manual intervention basically. And what deep learning is doing is that it more or less has everything in one step. So yes, you still have to decide on the architecture of the neural network, but this is more or less general, and there's not much you can do wrong, except your neural network is not complex enough, so it's too small, and you don't have enough data maybe. But at the end, you just tell it, look, there's a neural network, here's data, go for it. And the neural network will learn how to interpret your input and yeah, bring the algorithm, so the weights correct, construct the weights and correct the weights such that the output is correct. And the more you train, the better result becomes. Okay, good. So the example that we had also, I think now a couple of times already, is conversion from Celsius to Fahrenheit. So given whatever you have some given temperatures in Celsius, and you're interested in how does it look like in Fahrenheit, and then you know that there's at least one more scale of temperature, so you want to calculate from one to another. So what one would do usually is that one looks up the formula on how to actually calculate that. So if you want to calculate Fahrenheit, then you take the Celsius, you multiply with 1.8, and then you add 32 to it, and then you have the Fahrenheit value. But maybe you don't have access to Wikipedia, or you just can't find the formula or so. So you want to do this conversation with a machine learning approach. And then what you would do is you would collect data. You have a Celsius thermometer and a Fahrenheit thermometer, and then you would put both next to each other. And then every day or every hour or every minute, you go outside and look at these two thermometers, and then you create this data on the x-axis the Celsius and the y-axis the Fahrenheit, and you get this kind of data set here. And this is now basically similar to the data set we just used in this super simple first example. This is now what you can use to do some what we call regression, or to train some regression algorithm. And the regression algorithm, the linear regression algorithm, that's what we discussed a couple of times already, we'll find this kind of red line here. This is then the solution. And this means, okay, if I have 0 Celsius, then I go up until I hit the red line, and then I go left until I hit the axis, and then I know what this is in Fahrenheit. So this is then our model here, the red line, and we can find it using algorithms, for example, linear regression. And the word linear tells you that, yeah, well, it is actually a line. And therefore, the main problem with this approach is if we go for the classical machine learning, that we have to define first how our model should look like. Should it be a line? Should it be something sine or cosine-like? Should it be something super complicated? And once I have chosen the model, whether it's a line or something more complicated, then I can parameterize it, meaning the line goes from here to here or from here to here, or whatever the position in space is. Or if I go for some higher models, then how large should it be from the distance here, or what should the amplitude be, and so forth. So I need to learn the shape. But first, I need to make sure that I have a model, again, a line or something else, and then I can parameterize or the shape, basically. And again, in the neural network sense or perspective, I need to create an architecture of the network. How many nodes should be there? How many layers should be there? And I need data. And that's it. And in theory, a neural network, again, if it's complex enough, can fit any data, no matter how complicated it is, no matter whether it is super high dimensional, as many pixels in an image, or speech, or other tasks for even generation of things, as we also saw last time. So it doesn't matter what the data is, a neural network, in theory, can learn it. The main problem is this training approach and finding maybe a complex enough architecture, but the architecture is not necessarily the limiting factor. So if the architecture is complex enough, you can do whatever you want if you have enough data. And if you have enough data is a big problem, because in practice, it means that if the neural network is quite complex and the data is quite complex, you need millions and millions and millions of data points for the training, and usually you just don't have that. And that limits the whole thing then again, because oftentimes you don't have this much data, you just have, say, a couple of hundred data points. And then usually large neural networks are not usable or suitable, because the error, as you saw in this first example, it will be just too big. It will learn something and it will learn some of the structure, but it will still have large errors. Therefore, what you really want to do is that you see, if I don't have too much data, then you maybe go back to classical machine learning and try out a couple of these models, but at least they're more or less specified. And if you really have enough data, then you can go to the neural network sense. Okay, good. So that's what we already said. If the network is complex enough, then you can fit more or less any data. The neural network that we saw in the first example was this one. We had one input node, we have one middle node, had hidden layer with one node, and we had an output node. And what we will see now in the next example is what if we take more nodes in the hidden layer, and what happens if we take 2 hidden layers also with more nodes. How good will our result be if I want to learn some data, and what can I do to make it even better, maybe. For this, we go to our next notebook. There was, before we do that, one question in the chat. Does pyTorch try to build up equations to do the job? No. pyTorch really is there such that you can build this architecture, as I'll show in a minute. And under the hood, it really learns only the weights, or it gives you the tools such that these weights can be learned, but there is no real trying to mimic an equation or build up equations. However, there are neural networks that really try to do that, but that's a very different architecture than the ones we're discussing today. Next question, is there a standard method to determine whether you have enough data for specific methods? Yes, there is a standard method. I didn't touch on that last time, and will also not today. The short answer is you have a data set to train on, and you have a data set to validate your learned method, which means you train on one part of the data, and then you check on the data you didn't use for the training, how good that is. And in the normal case, when you train a network on both of these data sets, it will become better and better. So your model learns the structure of your data, And since your validation set is similar to the structure of your training data, it also gets better. And then there will be a time where your neural network will become even better on the training data, but worse on the validation data. And this means that now it starts to be too specific to the real input part, but doesn't generalize anymore. So it cannot predict anymore, well, at least data it hasn't seen as a training before. And that's the point where you then stop learning. And therefore, you have the network that is still being able to generalize. And on the same idea, you can check whether your network is already able to predict data it hasn't seen before based on the training. And if this is so far off than what you accept to have as an error, then you also know that you don't have enough data yet. But if you have this idea of, okay, the data that I haven't used in training is well enough predicted at the moment, and this error that is made there is acceptable for me, then you know you did have enough data for the training. Good. Now, next example. I'll go through step by step, but skip over the parts we already had. So in the first part, we import again all the necessary libraries. We check before we do this whether we are still in GPU or we are not. So we click here to change to GPU. It tells me now that I need to close my old session because I'm not paying, therefore I can only use one GPU at a time. So I'm trying again. I'm trying again to change my runtime. It is now on GPU. That's good. Okay. Then once this has stopped generating or loading, I will now create. So this part here is to create. You see the formula from before, 1.8 times x plus 32. I generate now data. And the data looks like this. So this is similar to our Fahrenheit Celsius graph. So the real function is this one here. And then I generated data that are a little bit noisy. So it's not exactly representing the real function, which is the red one here, but it's close to it. So we now have the blue data. And this blue data we will now use to train our models. And then we'll see whether we get this red line back. And the first thing we do is that we use some linear regression. That's what we did the last hands-on session, and also in the webinar before. And what we can see here now is that our model was also aligned, hence linear regression. The green line is what the model learned only from the blue data. So it was trying to find some line that is more or less in the middle of the blue data everywhere. And you see it's a little bit off. But the good news is from this one, you can actually directly extract the formula it learned. And you see the formula it learned is minus 1.7 times x plus 31.78, which is not exactly the one we put in. However, it's close. And you can also see on the visualization, it's not that bad. So that's now linear regression in a classical machine learning sense. We had to specify the model, and then we said, okay, for this model, please just put it now in space such that it's more or less matching the data. Okay. We can do that also with some nonlinear function here. So the nonlinear function is then something that is not a line, but it could be some curved one. We see this already here. So in green now is the nonlinear model has learned, and you see it's a little bit more curvy, and therefore deviating quite a lot here at the end from the red line. So if you have had another model that is the wrong one and the parameter that you learned it, you will find it doesn't work really nicely. Okay, and now we do the same idea for a neural network. So again, we get our imports here, our torch imports. We convert now the data from above. So this XY ones that we generate here. So the blue ones are now the data that we are using all the time for learning. We convert this to this tensor format that torch needs. And now we start with a very simple model. So that's exactly as we had before. We have one layer with one hidden neuron. So it looks like this one. So there's the input, one hidden neuron, and the output. So that's what we use. The rest is already as we saw before. So we construct our model, we define the loss function, we define the optimizer, we do the training. And then we see that it starts with a loss of 0.35, and this one goes down then until the loss is, oops, where are we? 0.06. And now what we can do is that we can visualize that, and we will find that the visualization is screwed up. Because what did I do wrong? I have the original data. Because there's something wrong here. I think this should be 5. Let's try again. A bit better. So it's sorry about that. And what you see is, again, the real function is the red one here. The blue one is the data that it learned. So the red line it did not see. The blue one it saw for the training, and the green one is what it spit out. That you can see that the green one is actually quite well going. We can make this a little better. Quite nicely representing the other one. I know it's better. And we didn't tell the network to be more or less a straight line or anything. It just learned it from the data. Question is, can we get a little bit better? We now have a bit more complex network where we have, again, 1 input, 1 output, and then we have now 10 in the middle, 10 neurons in the middle. We do the same thing. The building of network is, again, super easy. We now have a hidden layer of 10 nodes that we have in between. So input to the hidden to 10 hidden, and then 10 to 1 output. That's how you define it here. There's something called a ReLU activation function. It's not too important at the moment. It's just how these things are connected. We again train. We get a loss function that becomes better over time. That's good. We visualize it, and we find that now our model is more complex. So it also has some interesting parts here where it deviates from the data. However, if you look at the data in this part, because it only saw the blue dots here to train, it is actually not that bad. It is more or less in the middle of the blue dots. So given this data here that we trained with, it's not that bad. And then you could play around with it again and actually create more data in the beginning. So maybe we have 80 points now that we create. Let's have a look at it. So now we have much more data that is sampled. And then we again try with this second model here to, first we need to convert it again to the data that we can use. So here, so now we converted the new data points, and now we train the more complex model again. And we visualize it. And we see that now this green, that's what the model has learned, is pretty much exact on partly at least on the actual real data on the red line here. So the more data I put in, the better my results become. So I could now play even more and put now hundreds and hundreds of sampling points, and at some point in time you will see that the green line will be exactly on top of the red line because I have more data. So this is also to the earlier question: the more data you put in, depending on how much error you are willing to accept, this thing can become better and better and better. Okay, and then we can define an even more complex version here. So now we have 2 hidden layers. Again, the construction is again quite simple. So from input to the first hidden layer that has 10, then to the second hidden layer from the first to second, and then to the output. So again, looks like this: input, 2 hidden layers, and then to the output. And if we use this model now, then again, it trains a bit more now. I made it to train 1,000 epochs because it's more complicated now. And we can have a look at it and see that it's partly impressively well. And then at the end, it again deviates a little bit because then also the data is a little bit off here. And now you would go into this, what we call gray magic. Now you would play with the architecture of the neural network and the training times and the optimizer and the loss function and so forth to see what is your best outcome of the model. Good. So this showed you more or less how a training can be done, how simple it really is to train it and to build it also. And the last example of today will show you, and I will start it already because it takes some time to load all the data. And then I'll continue with the explanation. Check again. Good. And we tell it to start already. We don't do this, we don't do this. Starts. That looks good. Okay. Now, in the next example, we do image classification. And maybe while this is doing something, I will put this over. Image classification is also one of the things why deep learning network became so successful, because there was a lot of research went into all this. And the idea is, excuse me, that you have a new network. And again, you put in an image, say a cat and a dog here, and you let it run through the neural network. And then the output is as we expected here, because the cat is put in this cat. And the idea is that you train the network as before with this labeled data. So we had X and Y before, now we have images and labels. So we have this data here, we have the labels. So we tell network what it is, and then we improve it with more training or another optimizer and so forth until it gives us the correct predictions here. And again, this model training needs to be done only once, but it can be very time and resource consuming. So with images, it can take well over days and up to weeks, depending on how fast your GPU is and how many images you have. But this is really quite resource intense. But once you have it, you can just use it for prediction. You will never have to train it again. Okay. And in the approach that we are doing now in this demo that I will be showing you is that we will take already a model that has been trained on images. So the model already is in a state in which it can, at least in principle, detect and classify images. But it is not very well yet fine-tuned, as we call it, for cats and dogs. So we take a model that has seen a lot of images before and is able to kind of classify them. And we want to make it even better on cats and dogs. And this is a point where more or less you can maybe think of whatever application in your personal field, if you're dealing with images at least. So you can take a network that knows how to classify images, but is not very good at a particular domain. And then you can take this domain that you're interested in, I don't know, items from a warehouse or so, and then train it as particularly for these images. And then your neural network becomes better and better on this particular domain you're interested in. And the training that's been done here for hours and days and weeks, you can just download from the internet, and you can do this for images, for language, for waves, so for frequencies, so speech and so forth. So these are all available. And this is called transfer learning. So the idea is really that you have already some network that was trained on a lot of images. This is your first data set, you train a model with it. This you can download now, and then take another data set. In our case, it will be dogs and cats. You use this data set to improve basically the first model, because the knowledge that you transfer, and you have a new version with what you learn and what you use then later on. And this is called transfer learning. And what we will do in the notebook or demo now is that we have some model. We take some called, it's a ResNet34 model, which is a particular architecture of a neural network. This has been trained on images, 10 categories, I think, in the Cypher10 data set. This network we use, and then we adjust it with the images that we get from another data set, which is done by some Oxford team. And this data set only contains cats and dogs. So it has nothing else, just cats and dogs. And the idea is then, okay, if I download this model, then how well can it then be used, or how well can it be done to generalize on my data that I'm having. Okay. Good. Okay, there's an error here, but that doesn't matter. So what did we do? At the beginning, we installed some libraries that were not on the system yet. Then we imported the libraries that we need. In this case, we imported a library called FastAI, which is just another library sitting on top of pyTorch and the others and gives you even easier methods to deal with neural networks. Then we downloaded, and that was the line that went wrong here because it couldn't concatenate these two strings. It downloaded the data from this URL here. So you get to this one, and then you see the data set, and you see that this is basically all data that I have in the data set. So downloaded that. It unzipped it to this computer on which my notebook is running. Then we had to tell it how to get the labels, basically, and not too important, but what happens here is that all the cat images have a capital letter in the beginning of the file name, and all the dog images have a small letter in the file name. So that's how I can tell my neural network on what is a cat and what is a dog without using explicit labels anymore. Then I loaded all the images. So I said, okay, this is the path on which they're unzipped at my computer. That was also going back to the question earlier, how do you know when to stop the learning or whether it's good enough? So I told it I need a 20% of the data for its validation set that I mentioned. And the last thing I did, and this is often important in image analysis, I resized all the images to the same size. So with this command here, I can do everything what I just told you, including this resizing. So this is the pre-processing and loading of the images that I had. And that's now basically under this, there's hundreds of lines of code that are actually coming from the library. I now said, okay, give me a new model, in this case, a vision learner, so a neural network that can do image analysis. Here is my images from before. This is the network I want to use, this is ResNet34, and my metric, that's what we had before. So how to determine which error I want to use is the error rate. So how many images are actually going still wrong or are still good. And then we are getting towards 1 o'clock, but this should take 20 more seconds here. It's now doing the fine tuning. So it's now just using the data that I used, so the cats and dogs from this data set here. It trains now a pre-trained network with only my cats and dogs. And then it goes over another pass. And then at some point it should say, I am done now. And hopefully 3 seconds. Yo. Now it's trained. So again, it's a pre-trained one. Now fine-tuned on our cats and dogs. Now I can use an image to train it with. I can upload an image that I want. I'll take this cat here. And I tell it to perform the prediction. It tells me, oh, this is actually a cat. And then last example, I also have a dog image here. This one, I use this and ask it, is it a cat or a dog? And it said, well, it's not a cat, therefore it's a dog. And it shows me also the dog. Good. This was a very fast run through the notebook for the image classification. But again, what you should have seen is that using or refining a already existing image deep network for, in this case, cats and dogs, is just a matter of 10, maybe 12 lines. The upper part was only to download the data and prepare it and so forth. But this is basically everything you need to get a full-fledged deep learning network or model with which you can do image classification for whatever domain you're in. You can have multiple other images, not only cats and dogs. You can have 7, 10, 15 domains or different types and really start doing image classification, for example, or whatever else classification with the deep learning network. So the main message was that you get the idea and that you see if you know these couple of lines or this couple of code commands, and then it's really easy to do all that. And it should maybe also take a little bit the fear from, oh, wow, it's also complicated, I can never do that. Sure, one needs to get the basics correct, and needs to get a little bit of understanding. But at the end, even running some really complex and complicated tasks is a matter of lines these days because we have these really good libraries available today. And with that, I'm done with my card. Happy to answer questions. Material will be available, is available. So even if you have questions for that material, if you go through it again, just write me an email or contact me on any other channel that you have. And I'm happy to answer all these questions.